right, we're continuing with data representation. Let's take a look at the learning targets. Cambridge wants us to show an understanding of the basis of different number systems. They want us to use binary, denary, hexadecimal number bases. They also want us to use binary code decimal and ones and twos complement representation for binary numbers. Not a problem. We'll be able to do that. Not too difficult at all. Then it wants us to convert an integer value from one number base to another. So we have all these bases or all these forms that we're looking at. Let's go ahead and jump into it with binary coded decimal. What is binary coded decimal? It is where a single denary digit can be represented by 8 bits or 4 bits. It will usually tell you. If it doesn't tell you what they want you to use, you count the number of boxes. We'll take a look at an example in just a few moments. Now, it's often used when the denary value is a double-digit number or more. You can see these in clocks. You can also use or see binary coded decimal used in the display of a calculator. Now let's take a look at an example first using 8 bits, then we'll take a look at an example using 4 bits. So let's take a look at the number 93. Now I have two digits here. I have a 9 and I have a 3. Using 8 bits per digit, we're going to use a total of 16 bits or 2 bytes to represent this number. So to represent the 9, this would be my binary number, 0, 0, 0, 0, 1, 0, 0, 1. And that is because here, 1, 2, 4, 8. 8 plus 1 is 9. The rest of these would be 0. To represent the 3, I need the 2 and the 1. And I'm going to change mine to purple here. So 2, 1. That will give me 3. And the reason I'm changing the purple is because I use a lot of red and blue, and I don't want to confuse anybody. So to write 93 in binary coded decimal, we take our value for 9 and the value for 3, we put it together. The reason this is in two different colors is so you can easily distinguish from the 9 and the 3. That would be 93 in binary coded decimal using 8 bits. Now let's take a look at it using 4 bits per digit. We're going to use a total of 8 bits or 1 byte. Here's my value for 9 in binary. Here's my value for 3 in binary. I put them together and I get 9 and 3. So this right here I know is the value of 9. This is the value of 3. That is binary coded decimal. All you're simply doing is solving for each individual digit. It is basic binary. Going too fast, you could make a simple mistake. And we all make mistakes. It's no big deal. So let's take a look at these binary coded practice problems. Use the given boxes below to write the binary coded decimal value of 127. It doesn't tell us whether you use 4 bits or 8 bits. That could be a problem. Let's look at another one. Use the given boxes below to write the binary coded decimal value of 14. Doesn't tell us how many bits to use. That could be a problem. All right, so we have a set of boxes here. When I count the number of boxes, I see there are 12 boxes. Because I have 3 digits, I can't use 8 bits per digit. I would need 24 boxes. I have 12 boxes, which means I'm going to use 4 bits per digit. So if I'm using 4 bits per digit, my 4 bits are going to be the values of 1, 2, 4, and 8. My next set is going to be the same thing, 1, 2, 4, and 8. My next set is going to be the same, 1, 2, 4, and 8. The value I'm looking for first is a 1. Well, that's easy. I'm looking for the 1. Here's my 1. This would be my 1. Now I'm looking for 2. Not a problem. Here's my 2, which means the rest of these would be 0. And then my third set, I'm looking for a 7. Okay. Can I use 8 to get 7? Nope. That is a 0. Can I use a 4? I sure can. Now I'm at 4. Can I use a 2 to help me get to the rest of the way to 7? Yes, I can. 4 plus 2 is 6. Plus 1 is 7. This is the binary coded decimal form for 127 using 4 bits. All right, let's jump down to the 14. They didn't tell us how many bits to use. Well, it can't be 8 bits per digit because I would need 16 boxes. I only have 8 here to work with. Now, the reason I'm using 4 bits per number is because, or as the examples, is because most likely in past tests, that's what Cambridge gives the examiners. So let's start with our values, 1, 2, 4, and 8. And you don't need to write these values above the boxes. It takes about 15 seconds, and it helps you to easily prevent an easily error, or a most common error that's done. People put a 1 or a 0 in the wrong place, and they mess it up. take the extra 15 seconds, write the value above the boxes. It'll make it so much easier. All right, so we're looking for a 1 and we're looking for a 4. Well, I can't use 8, 4, or 2 to get to 1, but I can use my 1. We're done. Now I'm looking for the 4. And here's my 4, which means the rest of these are zeros. And my binary coded decimal value of 14 is 00010100. And we are done with binary coded decimal. And now we're on to the next, ones complement. So what is ones complement? If the binary number is positive, the complement is a negative. It goes together. It's the opposite, if you will, of what it is. So how do I know if the ones complement number that I've been given, how do I know if it's negative if it's in binary form? The most significant bit, the leftmost bit, has to be a 1. If it's a 1, we know it's given us a negative binary representation. Now, if the binary number is negative, the complement would be the positive. Well, how do I know if it's positive? The most significant bit, the leftmost bit, is a 0. That's how we know. So here's the ones complement rule. It's very easy. When finding the ones complement, all you have to do is get the binary value and you invert every single bit. This means all the ones change to zeros, all the zeros change to 1. So let's try a couple examples. So find the ones complement of 23 using 8 bits. Find the ones complement of 17 using 8 bits. Okay, so we have our boxes here. Let's go ahead and fill out these values. 8, 16, 32, 64, 128. Okay, so we're looking for 23 and got some room over here to work with. I can't use 128. I can't use 64. I can't use 32. I can use 16. So let's go ahead and minus 16. That comes out to 7. I can't use 8 to get to 7, but I can use 4, 2, and 1. 4 plus 2 is 6, which leaves me 1, and then I put the 1. Now, that is not the answer, because it wants us to find the ones complement of 23 using 8 bits. This is positive 23. I know that because I have a 0. So to find the ones complement, negative 23, all I have to do is change all the ones to zeros, all the zeros to 1, which means this 1 becomes a 0, this 1 becomes a 0, this 1 becomes a 0, this 0 becomes a 1, this 1 becomes a 0, this 0 becomes a 1, this 0 becomes a 1, this 0 becomes a 1. This is equal to negative 23 in ones complement. How do I know this is negative 23? How do I know it's a negative number? Because this leftmost bit is a 1, which means it is negative. All right, let's find the ones complement of 17 using 8 bits. So I'm going to use the same values I did up here. I can't have 128. I can't have 64. I can't have 32. I can use 16. And then I'll also need 1, which will get me to 17. That is not the answer, because it wants us to find the ones complement of positive 17. How do I find the ones complement? I simply invert every single bit. This 1 becomes a 0. This 0 becomes a 1. This 0 becomes a 1. This 0 becomes a 1. This 1 becomes a 0. This 0 becomes a 1. This 0 becomes a 1. This 0 becomes a 1. This is equal to negative 17. So this is equal to negative 17. I know it's a negative because my leftmost bit is a 1. This is positive 17. How do I know this is positive 17? Because this is a 0. When I add 16 plus 1, I get 17. It is that easy. Now, what if you're given a negative value? Not a problem. When given a negative value, the ones complement would be a positive. Just find the positive value in binary like you normally do. So, find the ones complement of negative 37 using 8 bits. Not a problem. Find the ones complement of 16 using 8 bits. Not a problem. So all we need to do is find the value of 37, positive 37. So I write my numbers above here. And if they give me if they give it to me in ones complement, no problem. I just invert all the ones and zeros. I don't need 128. I don't need 64. I'm looking for 37. I do need a 32. That will help me. So I'm going to minus 32. I'm now left with 5, which means I need a 4 and a 1. 4 plus 1 will give me 5. These become zeros, and I'm done. Because this is a positive 37, which is the complement of negative 37. Jumping down here, I need the complement of negative 16, which is 16. I don't need 128. I don't need 64. I don't need 32. And here's 16. The rest of these become 0. This is the ones complement of negative 16, simply the positive value. I know this is positive because it starts with a 0. Here's another 0 down here. I know that is a positive binary number. It is that easy. Okay, so let's talk about the 0. With ones complement, you still end up with a positive and negative 0, just like we did earlier in the previous podcast. So my positive 0, the ones complement of positive 0 would be a negative 0. So I have some boxes. What would positive 0 be? Well, my first digit must show it's a positive number with a 0. Well, what's the value of 0? Zeros, all zeros. So that is positive 0. If I want to find the ones complement, which is negative 0, I have to invert every single bit, which means every single 0 becomes a 1. So all zeros would be a positive 0. All ones would be a negative 0. Let's talk about 2's complement. Now, 2's complement eliminates the positive and negative 0. You're going to get 0. There is no positive and negative 0. 2's complement makes binary arithmetic, addition and subtraction, much easier, which we'll be taking a look at in the next podcast video. Now, in 2's complement, how do I know if it's negative? You follow the same rule. If the most significant bit, which means the leftmost bit, it's a 1, you know it is negative. If the binary number is negative, the complement is a positive. In 2's complement, how do I know if it's positive? The most significant bit, the leftmost bit, if it's a 0, it's a positive number. Same rules apply here. The only difference is when you're converting. So when finding the 2's complement, you do not invert every single bit like you did in 1's complement. Here are the steps if given a positive binary value and you have to find the complement, which means you need to find the negative value. It's not difficult. Find the positive binary value. Once you find the positive binary value of the denary number, you're halfway done. The hard part's over. You're going to start from the right, moving left. You're going to ignore all zeros until you arrive at the very first one in your binary number. You're starting from the right, moving left. You're going to ignore all zeros until you arrive at the very first one. When you arrive at the first one, you're going to leave that one a 1, and you're going to invert all the remaining bits to the left of the first one. All right. So we're going to look at some practice problems. This is the complement. This is a 2's complement format for 8 bits. You'll notice the leftmost bit is negative 128 when using 8 bits. If the leftmost bit is a 1, we know it must be a negative number because if this is a 1, I can't add all these up and get higher than a negative number. If this is a 0, that means I don't have negative 128. I'm going to wind up with a positive number. That's how it works. So let's find the 2's complement of 91. Well, the 2's complement of 91 is negative 91. The first thing I need to do is find the positive binary value. Do I need negative 128? No, I don't. Do I need 64? I sure do. So I'm going to minus 64. 11 minus 4 is 7. And then 8 minus 6 is 2, using some basic math. I don't need 32. I do need a 16. So I'm left, now that I've factored in the 16, I'm still looking for 11 values. I can use an 8. That means I'm going to wind up with 3. I can't use a 4. I can use a 2 and a 1. Now, that is 91. I need to find the 2's complement, which means I need a negative 91. I'm going to start from the right, and I'm going to move left, 1 digit at a time. So start from the left, go from left to right, ignore all zeros, stop when you get to the first one. Starting from, this should be right to left, sorry. Starting from right, and you're going to go left. Didn't even copy the rule down correctly, but that's okay. Ignore all zeros, stop when you get to the first one. Well, there are no zeros when I'm starting from the right. I wind up with the first one. After the first one, you invert the rest. We're going to keep this first one. I have arrived at my first one. Now what I'm going to do is invert the rest of them. This 1 becomes a 0. This 0 becomes a 1. This 8 becomes a 0. This 16 becomes a 0. This 32 becomes a 1. This 1 becomes a 0. This negative 128 where I have a 0 becomes a 1. if I add negative 128 plus 32 plus 4 plus 1, it'll come out to negative 91, because this is the 2's complement. It'll come out to negative 91. 32 plus 4 is 36. 37, 128. Negative 128. Adding 37. We're going to wind up with negative 91. You can check your answers with these, but if you find the positive value, you can invert it. If you're given the negative value, invert it. Okay, so let's take a look at these 2's complement. Show the value of negative 121 in 2's complement. Find positive first, then follow the rule. So we're given a negative number here. We need to find 121, and that's all we need to do. Or we need to show the value of negative 121 in 2's complement. Ooh, okay. So the first thing we're going to do is find the value of 121, because that's easy. And then what we need to do is simply follow the rules. Well, I don't need negative 128. I do need 64, and I do need 32. 64 plus 32 gives me 96. So I still need to find, I need to get to 121. I need 16. That gives me 112. And now I need 9, which is, because 112 plus 9 is 121. Okay, I have found it. Now, to show the value of negative 121 in 2's complement, if this is 121, this will be negative 121. And all I do is follow the rules, starting from right to left. We're going to ignore all the zeros till we get to the first one. Oh, look, we found our first one. There were no zeros to ignore. Now I invert all the zeros to ones and all these ones to zeros. And this is how we wind up with negative 121. This is negative 121 in 2's complement form. Negative 128 plus 4 plus 2 plus 1. 4 plus 2 plus 1 is 7. Negative 128 plus 7 is negative 121. Show the value of 48 in 2's complement. Easy. 48 is a positive number, so the leading must be a 0. Do I need 64 to get to 48? I don't. Do I need 32? Yes, I do. Now I'm looking for 16, because 48 minus 32 is 16. I did it a little backwards up here. You can do it however you want. Oh, here's a 16. And this is 48 in 2's complement. So when you're looking for a negative number in 2's complement, don't worry about trying to add negatives to positive. That's just going to waste time. Simply find the positive value, then invert. If you're looking for a positive value in 2's complement, easy. All you do is find the normal binary number. Just make sure that negative 128 is a 0. Otherwise, you're going to wind up with a negative number. All right, let's talk about hexadecimal. Hexadecimal is known as base 16, and there are 16 values. The first 10 values are 0 to 9. You might be saying those are 9 values. No, you're forgetting the 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the first 10 values, which means we have 6 left. We can't use 10, 11, 12, 13, 14, 15, because 10, 11, 12, 0 all the way to 15, because 0 is a value, 0 all the way to 15, that's not hexadecimal. That's the denary or decimal system. So we can't use 10, 11, 12, 13, 14, 15. What we have to use are letters, and we use the letters A to F. Those are the next 6 values. Now, each hexadecimal character is written using 4 bits. You must have 4 bits when you write a hexadecimal character. There are no exceptions to that rule. So let's practice that first, calculating how many bits we need for the following hexadecimal problems. So how many bits are required for 4A? Well, how many hexadecimal characters do I have? I have 2 hexadecimal characters. I have 4, and I have the letter A. There are 8 bits. 4 bits for the 4, 4 bits for the A. 6, 7. Now this is hexadecimal. This is not read as 67. It's read as 6, 7 because it's in hexadecimal. How many bits do I need? Well, there are 2 hexadecimal characters, 6 and 7. This is 8 bits. What about EFE? There are 3 hexadecimal characters, which means I need 12 bits. What about FGG? That looks a little strange. This is invalid because F is the highest value you can have. Looking at this one, G's don't exist. Because it's base 16. F is the value of 15. You may be saying, yeah, but G is 16. No, it's not. Please do not forget that 0 is a value. 0 to 9 are my first 10 values. A to F are my next 6 values. There are only 16 possible characters. 0 to 9 and A to F. G doesn't exist. If I see G or any letter that exceeds F, I know right away it's an invalid hexadecimal number. And you'll need that when we get to IP addresses. All right, hexadecimal to binary. We separate each hexadecimal character. We find the binary value of the hexadecimal character. Easy. If the hexadecimal character is 0 to 9, the value is itself. Super easy. If the value is A to F, we use the following values. What comes after 9? A. Well, what denary value comes after 9? 10. A is equal to 10. What comes after 10? 11. What comes after A? B. And so on. And we go all the way to F. C is 12. D is 13. E is 14. F is 15. That is the maximum value you can get with 4 bits. If you don't believe me, go ahead and give yourself 4 bits. 1, 2, 4, and 8. And let's see what the maximum value is. It's 15. 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 8 is 15. That's the maximum value you can get with 4 bits. And because each hexadecimal character uses 4 bits, the highest value we can get is F, which is 15. So this would be F. Okay, so let's do some practice. Convert 4A to binary. Okay, the first thing we're going to do is separate these. 4. And then over here, I'll write A. Give myself plenty of room to work with. Now, here it's 0 to 9. All I need to do is use 4 bits to find the binary value of 4. Well, this is going to be 1, 2, 4, and 8. Let me see if I gave myself some boxes. I might have needed some boxes. All right, we know we need 8 bits. I need to move this down. I need to give myself boxes, and that's okay. So we need 4 bits for the A, or for the 4. So 1, 2, 3, 4. 1, 2, 4, 8. Okay, I don't need an 8. I do need a 4. So my hexadecimal starting 4 bits is 0, 1, 0, 0. But then I need to convert that A. I'm going to have 4 bits for the A. 1, 2, 4, 8. Okay, now I got to think about A because it's not a denary value. So I can't use 9 because, well, it's a letter. What comes after 9? 10. What is represented by 10? A. So I'm looking for the value simply of 10 here, which is 8 plus 2. So my hexadecimal, or my binary value for 4A is 0, 1, 0, 0, because the 4 came first, followed by 1, 0, 1, 0. That is the binary value of 4A. All right, let's try another one. E9. Okay, we know we need 8 bits because we have 2 characters. Let's do E, and then let's do 9. We know we need 4 bits, so I'm going to give myself 4 spaces. I'm going to take an extra 3 seconds to write out the value. If you're checking the time on the clock, it may be 4 seconds. I don't know. I'm just guessing here. Okay, so let's start with E. Okay, E is not a number. So looking at so we go 0 to 9, then we start with numbers. What comes after 9? 10. I know A is 10. What comes after A? B. B is 11. What comes after B? C. C is 12. What comes after 12? 13. 13 must be D, which means E is 14. To get to 14, I need an 8. 14 minus 8 is 6. To get 6, I add 4 and 2. So my starting binary value of this hexadecimal character E9 is 1110. That is the E. Now I need to find 9. I need an 8 and a 1. 8 plus 1 is 9. My last 4 bits are 1, 0, 0, 1. It is that easy. Okay, what about if you're going from binary to hexadecimal? You separate the binary number into groups of 4. Solve for each group of 4 and use the corresponding hexadecimal character. Here's a couple examples. So we have this one. All we're going to do is separate this into groups of 4. There, it's separated, easy to read. We're going to separate this one, easy to read. And we're going to separate this one. Now it's much easier to read. So this is a 1, this is a 2, 4, 8, 1, 2, 4, 8. And I'll just use these values going the rest of the way down. So this is a 1. So I have 1 plus 8. That equals 9. This is a 9. That easy. So here we have 4 plus 2 plus 1. 4 plus 2 is 6 plus 1 is 7. The first one, hexadecimal characters, is 7, 9. Let's take a look at this one. We have an 8. Well, that's easy. That's simply an 8. Here we have 8 plus 4 plus 2 plus 1. This is equal to 15. Okay, I know I can't use 0 to 9 here because 15 is not 0 to 9. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So if I'm counting in denary, I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If I'm counting in hexadecimal, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. F being my maximum value. Down here, I have a 2 and 8, which is a 10. So this is a 10. This is a 10. And that is simply A, because A is 10. All right. What about this number? Is this solvable? What if I have 1, 1, 1, 0, 0, 1? When I start separating it in the groups of 4, 1, 2, 3, 4, I only have 2 bits here. Is this solvable? Yes. There's only 6 bits. When I separate them, I wind up with these two sets of numbers, 1, 1 and 1, 0, 0, 1. That's what I wind up with. But remember, I need 4 bits per hexadecimal character. The 1, 1 might seem like a problem because I need 2 more bits. The value of 1, 1 is 3. If I start here, 1, 2, 1 plus 2 is 3. Can I add 2 more bits and still keep the value of 3? Yes, I can. The 2 additional bits I need to add can have the value of 0. To make it 4 bits and not change the value, I can have 0, 0, 1, 1. So I still have the value of 3, but by adding a couple zeros, I get my required number of bits and I did not change the value. So we can solve it. Let's convert it to hexadecimal. So we have this right here. I start separating the groups of 4. This is not 4 bits. So I need to convert this 0, 0, 1, 1. And then over here, I have 1, 0, 0, 1. Now that I have my 4 bits, all I need to do is work this out. So we're going to convert this to hexadecimal. What is 1, 0, 0, 1? 9. Move this over here. What is 0, 0, 1, 1? 3. Now I can solve it by having the correct number of bits. And I'm pretty sure that is all that we're going to do. If you have any questions, you can post a comment below. We'll see you guys in the next video, unless there's another slide. But I think that might